study about dimensions of physical quantities. The nature of a physical quantity is described by its dimensions. All the physical quantities represented by derived units can be expressed in terms of some combination of 7 fundamental or base quantities. These base quantities are the 7 dimensions of the physical world, which are denoted with square brackets. Representation of 7 fundamental or base quantities by its dimensions. On the left hand side of this table, we have physical quantities, and on the right hand side, we have dimensional representation. For length, we have capital L written inside square bracket. Similarly, for mass, we have capital M. For time, we have capital T. For electric current, we have capital A. For temperature, we have capital K. For luminous intensity, we have small cd. And for amount of substance, we have small mol. Dimensional representation of volume. Consider a cuboid having length L, breadth B and height h. Then volume equals to length into breadth into height. From figure, we get capital V equals to L into B into h. Now, dimension of length equals to L, dimension of breadth equals to L, and dimension of height is also equal to L. Dimension of volume is given by L into L into L, which is equal to L cube. Volume is independent of mass and time. Then, for mass dimension, m raised to the power 0, for time dimension, t raised to the power 0, we can represent volume along with mass and time as m raised to the power 0 into L cube into t raised to the power 0, which can be written as inside square brackets m0 L cube t0. Similarly, we can derive the dimension of force. We know F equals to m into a, which is mass into acceleration. This implies force equals to mass into velocity by time, which implies force equals to mass into length by time divided by time, or force equals to mass into length by time square. Taking fundamental dimensions of length, mass and time, we have dimension of force is represented by m into L by t square, which is equal to m into L into t raised to the power minus 2. Therefore, dimension of force is mlt minus 2. Dimensional analysis and its applications. A thorough understanding of dimensional analysis helps us in deducing certain relations among different physical quantities and checking the derivation, accuracy, and dimensional consistency or homogeneity of various mathematical expressions. Checking the dimensional consistency of equations. We can test the dimensional consistency or homogeneity of the equation x equals to x naught plus v naught into t plus half at square. The dimensions of each term may be written as for x it is L, for x naught it is L, for v naught t it is L t minus 1 into t, which is also L. Half at square equals to Lt minus 2 into t square, which is also L. As each term on the right hand side of this equation has the same dimension, hence this equation is dimensionally correct equation. explanation for the distance x traveled by a particle or body in time t, which starts from the position x0 with an initial velocity v0 at time t equals to 0 and has uniform acceleration a along the direction of motion. The magnitudes of physical quantities may be added together or subtracted from one another only if they have the same dimensions. Velocity cannot be added to force, or an electric current cannot be subtracted from the thermodynamic temperature. This simple principle is called the principle of homogeneity of dimensions. In an equation is extremely useful in checking the correctness of an equation. Deducing relation among the physical quantities. The method of dimensions can sometimes be used to deduce relation among the physical quantities. Example: let us see the solution. The dependence of time period t on the quantities L, G and M as a product may be written as capital T equals to K into L raised to the power X, G raised to the power Y, M raised to the power Z, where K is dimensionless constant and X, Y and Z are the exponents. By considering dimensions on both sides, we have L0, M0, T1 equals to L1 raised to the power X, L1 T minus 2 raised to the power Y, M1 raised to the power X, which gives L raised to the power X plus Y, T raised to the power minus 2Y and M raised to the power Z. On equating the dimensions on both sides, we have x plus y equals to 0, minus 2y equals to 1 and z equals to 0, so that x equals to 1 by 2, y equals to minus 1 by 2 and z equals to 0. Then capital T equals to k L raised to the power 1 by 2, G raised to the power minus 1 by 2. We know that k equals to 2 pi. Therefore, T equals to k under root of L by G. Therefore, T equals to 2 pi under root of L by G.